Hello all. We continue talking about the heuristic algorithms. In this video lecture, we are going to talk about the types of heuristic algorithms, and then we will start learning construction heuristics, and we will make some examples, some application examples of these construction heuristics. So, when we consider heuristics, we can classify them into several categories. You may include some more categories into this classification, but mostly we can talk about construction heuristics, improvement heuristics, and meta-heuristic type algorithms. Okay. So construction heuristics are the heuristics in which you generate a good feasible solution from scratch. Okay. You don't initially have a solution, and by following the steps of this algorithm, you construct a good feasible solution. So greedy heuristics are most well-known types of construction heuristics. Or there may be some heuristics which are based on mathematical modeling. So for example, you have an integer programming formulation which takes a lot of time to solve to find the optimum solution. But what you can do, you can just solve the LP relaxation of the problem. You get a solution which is not integer, feasible. Then you can somehow modify that solution, round the non-integer variables to up or down, and try to construct an integer feasible solution. It can be a construction type heuristic. Okay, for improvement heuristics, the main idea is this. You initially start with a solution, you have a solution, and by searching the neighboring solutions of this current one, you try to improve its value. So we will talk about this in detail when I say neighbor solutions. We will talk about what's neighbor and etc. Okay, but in this improvement heuristics, the basic idea is this: starting from an initial solution, at each step you move to a new solution which is better than the previous one. We can also talk about meta-heuristic algorithms. In fact, meta-heuristic algorithms are also improvement type heuristics. Some of them includes their construction phase as well. But basically, in meta-heuristics, different than the improvement heuristics, you can allow non-improving moves in order to escape from local optima. Again, we will talk in detail on this, but the thing is, in improvement heuristics, you just move in the improving direction, and whenever you find a solution, you encounter a solution and you look the neighborhood of that solution. If there are no good solutions than the current one, then you stop. But in meta-heuristics, you don't stop at this point. You continue in a non-improving direction in order to escape from, if it's a local optima, escape from that local optima, and with the hope of finding a better solution. Meta-heuristics algorithms usually are inspired from different phenomena, different applications, and different processes in it. Can be from the nature. Okay. For example, one of such algorithms is the tabu search. It's a well-known meta-heuristic algorithm. We will talk about it in detail. And also simulated annealing, which is inspired from the annealing process of the metals. And another algorithm which is inspired from the environment and the evolution, which is called genetic algorithms. Also, there are particle swarm optimization and colony optimization, and there are tens, maybe hundreds of different types of meta-heuristics currently. In this course, we will talk about tabu search, simulated annealing, and genetic algorithms. As I mentioned, in construction heuristics, in constructive type heuristics, you start from scratch, and step by step you go to a feasible solution, but of course at each step, while taking a step, you consider the objective function value. Therefore, at the end, you find a good feasible solution. You try to find a good feasible solution. In improvement heuristics, on the other hand, you start from an initial solution. Okay, this initial solution can come from a construction heuristic. And then starting from this solution, you move to a neighboring solution. And you compare this neighboring solution with the previous one. And you try to maintain the feasibility of the solution and try to improve the objective function value. Many construction type heuristics are greedy. Why they are called greedy? Because when they will make a new decision, if there are some alternatives for this decision, they always select the one which improves the objective function value the most. So they make the best choice among all alternatives. But they are not looking, usually they do not look ahead. They just consider the current step. They will not try to evaluate what will happen in the following steps. So in this sense, they are myopic. They only look one step ahead and make the decision so that they select the best decision in that step. For this purpose, they are called greedy. So I will give you some examples. The first example will be from a simpler problem, which is the knapsack problem. We already formulated this problem. And I will give you 3 different alternative construction heuristics for the same problem. So it means that for a given problem, whether it's set covering, traveling salesman, knapsack, machine scheduling, whatever it is, you may develop a different algorithm, different construction heuristic. There may be many different alternatives, and it's just limited with your imagination. Okay, so you can develop even your own algorithms. Now I'm going to give you 3 alternatives, and we will solve the same problem using these 3 alternatives, and then we will compare this with each other. Okay, let's have a look at this first alternative. The steps of the problem, or the steps of this construction heuristics are given here. So these steps, these types of writing, we call it pseudocode. Okay. It is instructions that you need to follow to solve the problem. It is not in the syntax of a computer program like Java or C++, but basically when you have these steps, you can implement these steps directly in the computer. Okay, but they are simplified versions of those steps. So we call these pseudocode. Okay, the first step of the algorithm tells that sort the items in decreasing order of value. Okay, let's first remember the knapsack problem. In knapsack, we try to maximize an objective function, which is the utility. Okay, total utility or value. So in this example, in the table, we are given an example, and we have in total 10 items. So I'm going to call them I from 1 to 10. Okay, the value or utility of each item is given here in the table again. So we try to maximize this total utility, and our decision is whether we will place item I to our knapsack or not. So this xi is our decision variable, whether it is a 0 or 1 decision variable. If it is 1, it means that we take it to our knapsack. Otherwise, we didn't use that item in our knapsack. And our constraint is that this knapsack has a capacity, and in this problem the capacity of the knapsack is given as 210, and each of the items has their own size. It can be either the weight or the volume. So we want this total size of each item that we placed into the knapsack So I'm going to represent the size with SI. So this should be less than or equal to the capacity. This is the knapsack formulation, and Xi is a binary decision variable. Okay, this is the formulation. What we try to do, look, if you look at the objective function, we try to maximize the total value, the total utility. And if you look at these values here, for example, compare item 1 and item 2. The value of item 1 is 79 and the value of item 2 is 32. Which one will you prefer? According to this objective function, okay, you should prefer item 1 because it has a higher benefit. Then in this alternative one, this alternative construction heuristic, in the first step, we sort the items in decreasing order of value because first we want to place the items with the largest value. And according to this, if you look, this item 6 has the largest weight or value, which is 85. So it will be our first item. Then comes the first item with a value of 79, so it becomes our second order. And then the next item is item 10 with a value of 59, so it is in the third order, and etc. So in the first step, we need to sort them. In the second step, starting from the first item here, we will set the variable value to 1. So the first item is item 6. It means that we set x6 equal to 1. And then it means that we are taking this into our knapsack. It says calculate the remaining capacity, knapsack capacity. And look, the size of this x6, the sixth item, is 95. If I place this into my knapsack, now I initially had 210 as the capacity. And when I place item 6, I am using the 95 of it. So the remaining knapsack capacity will be 115. It means that I can use this remaining capacity to take some other items. Okay, during the steps of the algorithm, in the third step, it says that if the knapsack capacity is less than 0, it means that you place an item and the capacity reduced below 0. It means that you exceeded the capacity and then you cannot put that item into your knapsack. And this algorithm tells that if that's the case, take the last item out of the knapsack, okay, and then continue with the next item. If the capacity is not less than 0, but if there are no remaining items, it means that it's time to stop the algorithm. But if there are some remaining items still, which we didn't evaluate, then we need to return back to step 2 and consider those items. Okay, now let's use this algorithm to solve this problem. Okay, so the first step is sorting the items with respect to value, and according to that, this is the first item, this is the second item, this is the third item, and etc. So these are the sorted values, sorted items. Then we select the first item, which is S6, and set its variable value to equal to 1, right? And then we compare, we evaluate, okay, if this is 210 was our capacity, then we subtract the size of this item from 210, we found it's 115, okay, and since this is greater than 0, we still have remaining capacity, then we say that, okay, this is good. We can continue with the next item. Okay, so let me erase this part. Now we have the remaining capacity 115, and we already evaluated this first item, and we can continue. We will return back to step 2 and continue with the next item. And in the order, the next item is item 2. Okay, and in this step 2.I, we set the variable value equal to 1. Then we need to calculate the remaining capacity, 115 minus 85. So it makes 30. It means that we can still take this item. It's not less than 0. Okay, so we will set this value equal to 1, and the remaining capacity will be 10, and then we will return back to step 2 again. Next, we select the third item, this one, and we set its value equal to 1, the variable value. Then we set, okay, 30 minus 52, which is minus 22. So the knapsack capacity is less than 0. It means that we need to revert this change, which means that we need to make this 0 again. We cannot take this item because if we are exceeding the capacity, so its value will be 0. Okay, so we evaluated 2, we evaluated 3, then it's time for 4. Again, we will make its value equal to 1, and then 30 minus 48, it is minus 18. Since it's negative, we cannot take this item, so we will change again this one to 0. We are not taking. So we evaluated item 4. The next one is item 5, and we make it equal to 1. And when we make it equal to 1, 30 minus 55, it is minus 25. Again, it's negative. It means that we cannot take this item as well, and we need to make its value equal to 0, and we evaluated that one. For item 6, again, since this size is greater than 30, we cannot take it. For item 7, again, this capacity, this size is larger than 30, we cannot take it. Okay, for 8, now you see that the size is 26, which is less than 30, so we can take it. We will make its variable value equal to 1, and the remaining capacity will be 30 minus 26, 4. Okay, then we evaluated item 8. By the way, I am crossing out all items that we have evaluated, but it doesn't mean that when I cross, it doesn't mean that we didn't take. Whether we took an item or not is given by this row. Okay, so if we have a 1 here, it means that we are taking those items into the knapsack. If there are zeros, or if they are empty, basically empty means 0, we are not taking. And now the next item is item 9, but its size is greater than 4, so we cannot take that item. So it's 0, and we evaluated item 9. And for 10, again, its size is greater than 4, remaining capacity, so it is also 0. And this is the solution. We are just taking items 6, item 1, and item 2. And what's the objective function value corresponding to this? The objective function value is, for item 6, it's 85, the benefit. For item 1, it's 79. And for item 8, for item 2, it's 26. And when we add up all these, the objective function value is 196. Okay? So this is a feasible solution. It is a good solution. It's a construction heuristic. It provides a solution starting from scratch. So let's see another alternative. Now we are going to look at from a different perspective, and in fact very similar one, but we will develop a new construction heuristic. Again, let me remind you the problem. We are trying to maximize our utility ui times xi subject to the size should be total size of the items that we are taking with us should be less than or equal to the knapsack capacity. Okay, so what we can do, in the previous alternative we sorted the items with respect to their values, and starting from the largest one we try to place them into our knapsack. In the second version, what do? Look, we start by setting the variable value of each of the items equal to 1. Okay, you can see it from this table. We set each one of them equal to 1. Then we sort the items, assuming that we are taking all items with us now. But of course it will not be feasible because you will exceed the size. Okay, if you look, our knapsack capacity is 210, but if you take all items with you, the required capacity is 492. So it's impossible to take all of these items with you. But in step 2, what do? We sort the items in decreasing order of the size. Okay, decreasing order of the size. So look, this is the size. The largest size is for item 6 with 95. Then the second size is this, item 1 with 85. Then third one is this, item 9 with a size of 55. And fourth one is this. So we are sorting them in decreasing order, and this row shows you the sorted list. Then what do? In the previous heuristic, we were setting each variable value equal to 1 by 1 at each step. Here we set the variable value equal to 0 1 by 1, and then we calculate the required knapsack capacity. So 492. So we calculate the required capacity. And in fact, whenever this required capacity is less than the actual capacity that we have, we will stop. So it means that if the difference between capacity minus required is greater than 0, then we will stop. Okay. Otherwise, if this is not the case, we will return back to step 3 here. We will back to step 3 and repeat these steps. Okay, let's solve this problem using this heuristic this time. So we already completed the first 2 steps. We set all variable values equal to 1 and we sorted. Now in the third step we start from this item 1 and make its value equal to 0, which is this one. Okay, so we will set it equal to 0. And if we take this item out of the knapsack, what we will obtain, the required capacity is 490, and we are taking 95 out of this. Okay, so you will have 397, I guess. And this 397 is still larger than your available knapsack capacity. And we don't have this required capacity less than the actual capacity. It means that we need to return back to the beginning of step 3 and continue. Okay, so what did we do? We made this item 6 equal to 0 and the required capacity reduced to 397. Okay, we will continue with the next in the order, which is item 1. So this time we will set this variable value equal to 0. And when we do it, the required capacity reduced from 397 minus 85. So this number is 397, the previous required capacity, minus the size of the item 1 which we removed from the knapsack. Then, okay, we already completed item 1, we removed from the knapsack. Then we removed item 2 from the knapsack. The third one is item 9. So now we are considering removing this item. Okay, and when we remove it, the remaining capacity will be 312 minus 55. Okay, then we continue. We evaluated this 3, we removed it. The next one is the fourth one, which is this one, and we are going to make it equal to 0, and we will recalculate the knapsack capacity. So 257 is the capacity minus 52. If we do this, the remaining capacity will be 205. Now look, this 205 is less than my actual capacity. Then according to this step here, I am stopping the algorithm. It means that the solution is given in this row. Okay. And when you calculate the objective function, so how can we calculate it? We are going to add up these, which correspond to a variable value of 1. So 32 plus 47 plus 18 plus 26 plus 30 plus 40, and this total objective function value will be 119. Remember the previous case, it was 196, and this one is 193. And according to this solution, we can say that the previous algorithm provided a better solution. But of course, you cannot generalize this. This is only for this instance of the knapsack. We cannot just say the previous alternative is better than this alternative. Okay, this is just for this instance of the knapsack problem. Be careful with generalizing. Now let's see another alternative, alternative 3 for the same problem. Okay, now let's have a look at for a third alternative for the same problem. Let me rewrite the model here. We want to maximize ui times xi and subject to without exceeding the capacity. In the first alternative construction heuristic, we concentrated on this ui. We sorted with respect to ui and tried to place the item with the highest utility. In the second, we concentrated on the size of the item, and we tried to remove the item with the largest size from our knapsack. But in fact, you should consider both of these at the same time. What do we want? We want to place the item which has the largest utility with the smallest size. Okay, both of them at the same time. So just concentrating only on one of them is not enough for us. Therefore, in the third alternative, instead of sorting the items with respect to utility or size, basically we will sort them with respect to this ratio, value divided by size, meaning that ui divided by si. So for each item we calculate this ratio and we select the item with the largest one. Largest one means that it has larger utility because it is in the numerator, and it has smaller size because it's in the denominator. You can think about this ratio with this statement. We are trying to place the item which has the largest utility per unit size. Okay, so how do we calculate it? Let's have a look at item 1 here. The value of item 1 is 79 and the size of item 1 is 85. So basically we divide 79 to 85 and we find this ratio over here, which is 0.93. So for each of these items, we calculate these ratios, and those ratios are given in this column over here. Now in step 1, after calculating this, in step 2, we sort them in decreasing order of the ratio, which means that the largest one becomes your first item, the largest ratio, second largest, which is item 5, and third largest, which is item 10. Okay, so this row shows you the sorted list. Then in step 3 of the algorithm, in fact the rest of the algorithm is exactly the same as the first alternative. Starting from the first item, you try to fill this item into your knapsack. So you make the associated decision variable equal to 1. Okay, so let me clear this part here. What do? We make this value equal to 1. And then we calculate the remaining capacity. 210 was our initial capacity, and the size of this item 2 is 26. So we make this subtraction and then find the remaining capacity. And if you do this, you will find 184. Then the next one is, so we place this item. Since the knapsack capacity is not less than 0, we continue with the next one. The next item is this 2. So we make its decision variable value equal to 1. And then we recalculate the remaining capacity, which is 184 minus 22, 162. Okay, we place this also because the knapsack capacity is not less than 0. The next one is item 3. We make the corresponding decision variable equal to 1. Okay, and we calculate the remaining capacity, which is 110, 162 minus 52. It is still greater than 0. We continue with the fourth alternative. We make its value equal to 1 and subtract the size from the remaining capacity, which means that we also take this one. Then what do? We make the next one, which is 5, equal to 1, and then we calculate 62 minus 85, which is minus 23. Since it is less than 0 according to this, we revert this change and make this equal to 0. Okay, so we cannot take item 5 with us, so we just move to the next item. This is 0. The next item is this one, 6, and since this size is larger than the remaining capacity, we cannot take it. It's also 0. For item 7, we come to the next item, which is the 8th item, this one. Okay, so we can we can make its value equal to 1, and the remaining capacity will be 17, so it's positive, we can take it. The next one, this 18, it has a size of 21, larger than the remaining capacity, we cannot take it. Next one is 9, and its size is larger, so we cannot take it. So these are zeros, and this is the solution, and you can find the objective function value by just adding this 32 plus 47 plus 26 plus 40 plus 59. And when you do, you find the objective function value to be equal to 104. Now, if we compare all these alternatives with each other, we can see that alternative 1 has an objective function value of 196. Alternative 2 has the minimum objective function value, and alternative 3 has the maximum. So for this instance of Knapsack, alternative 3 is the best alternative. All of them provide good solutions. All of them provide, let's say, feasible solutions. But for this instance, only for this instance, alternative 3 is better than the first two alternatives. But we cannot generalize this. You need to make more tests to understand how they perform under different instances of the problem. And is this solution optimal? 204. The answer is we don't know. We cannot say yes, we cannot say no. The only thing we say is we don't know. It may be or it may not be. Sometimes the students confuse. So I say, for example, a statement, a true-false statement, and say that a heuristic algorithm can never provide an optimal solution, true or false. And they say this is true. But the thing is, that statement is not true. A heuristic algorithm may provide you the optimal solution. But the thing is, we don't know if that solution is optimal or not. The problem is that. Okay? So these are the three alternatives for the knapsack, and you can develop your own algorithm. As I said, the number of alternative heuristics is limited with your imagination. Everyone in the class can come up with a different type of heuristic. The thing is, some of those heuristics perform better than the others. In one instance, one alternative may be better than the other. In another instance, the other alternative can be better than that one. In order to compare these alternative heuristics with each other, you need to solve many instances and then look at the average worst case performances. So let's see another problem, a heuristic for a different type of problem. Now let's consider a well-known problem and develop a construction algorithm and solve an example problem for the traveling salesman problem. So in this example, we are given 7 cities and we are given the distances between each pair of these 7 cities. To reach from 1 to 2, 18, you can say kilometers or meters. From 1 to 3, it's 17. Okay, so there is a well-known algorithm, so-called the nearest neighborhood algorithm. It's very logical algorithm. Whenever you define this problem to someone and ask for how to solve it, people always come up with a similar algorithm. Okay, so how this algorithm works, let's see the pseudocode of this algorithm. It says that first randomly select a city and set it as the current city. By the way, in these pseudocodes, in reading these algorithm steps, as I said, it's very important to be able to read it by yourself without any explanations and to implement it. But in order to understand the steps of the algorithm, maybe it's first better initially to read all the steps till to the end. Even if you don't understand a step, what's going on in one step, try to read it till to the end, because usually in these algorithms there are loops and some step is written considering not only the previous step but also a later step, so that when the loop returns back to this step, that statement of the step can handle that situation as well. That's why please read till to the end such pseudocodes, and then in the second step read it again, try to understand each step. Okay, randomly select a city. So one of these 7 cities we are going to select, and we will set it as the current city. Then there is a loop here. You see, repeat until there are no unvisited cities. So it means that we are going to label the cities as visited and unvisited, and we will continue the loop until there are no unvisited cities. Okay, so what we will do, we will find the unvisited city that has the shortest distance with the current one. Okay. If equality, if there are two cities, two unvisited cities with the same shortest distance, then it says that select the city with the smallest index. Okay, sometimes in such algorithms, they give you the rule what happens under equality. Okay, if you are checking some condition and if there is an equality in that condition, what to do? In some heuristics, they give you such a rule. In some heuristics, they do not. If a statement is not made, then if there is an equality, you can do whatever alternative you like. You can select one of them randomly and continue with that. Okay, but here we have a rule, we need to follow this rule. And in the second step here, to I step, set this city as the current city and label it as visited. And then return back to this step 2 and continue until there are no unvisited cities. So let's solve this problem using this algorithm, very simple algorithm. We will start with one of the cities randomly. And let's assume that we are starting with city 4, okay, randomly. Then what we have? We are currently in city 4, so let me put a label over here so that we can understand we are dealing with 4. Okay, then it says that find the unvisited city that has the shortest distance. So unvisited cities are 1, 2, 3, 5, 6, 7. And I will look at this row over here. And inside this row, I will find the minimum. Of course, the minimum one is this 0, but it corresponds to the same. So I shall not consider this column. Okay, among the others, the minimum possible one is this one. Okay, there is no equality. It means that I am going to set this city 3 as the current city. So I'm going to write here current. Okay, current city is 3, and we are moving from city 4 to city 3. Okay, now we finished this 2-point-second case, and we will return back. There are still unvisited cities, so we just visited 3 and 4. We are currently at 3. Okay, so let me put an arrow here. So we are currently here. And it says that find the minimum unvisited city. Okay, so we shall look at now this row. And in this row, the minimum unvisited one is this one, which means that from 3 we will move to 5, and our current becomes 5 now. Okay, so let me make these adjustments. So we are currently in 5. Okay, so there are still unvisited cities 1, 2, 6, 7. I will find one of them. Okay, the minimum shortest distance with 5. So I have to look at this current cities row, and I see that we have this city 1 as the shortest distance. So now we are going from 5 to 1. The current city becomes 1. Okay, and we will find the shortest distance from 1 to other unvisited cities. So if you look at this one, and this one, we see that 2 has the minimum. So from 1 we are going to 2. So 2 becomes our current, and here I need to write 2 as the current, and from 2 I will look at the unvisited ones, which are this and this, and I see that 6 is the unvisited one, so 6 becomes the current one, sorry. Okay, so current is the 6, and since there's only one city remaining, I will move to 7. Okay, so this is how this algorithm works, but the question is, what is the objective function value corresponding to this solution? Let me write all these in this way. 4, 3, 6, 7. What is the objective function value corresponding to this solution? How shall we find it? So we will find it from this matrix. Okay. Basically, we will follow this route. From 4, we are going to 3. So the distance here is 4 units. From 3, we are going to 5, so the distance is 7. 5 to 1, the distance is 9. 1 to 2, the distance is 18. 2 to 6, distance is 23. And 6 to 7, the distance is 13. Sometimes students make mistake at this point. This is a tour, which means that from this last city you need to return back to 4. So sometimes they stop at this point, but sometimes in order to represent that we are returning back to the initial city, they write the initial city to the end as well. Or sometimes you don't write it, but basically you show it like this. So I have written it to the end, and the distance from 7 to 4 is 43. And the total objective function value, if you add up these, you will find 111. Okay, so this is the so-called nearest neighborhood algorithm. Of course, there are maybe different variations of this algorithm. In the next, we will see an alternative to this one. Okay, this is basically the same question and the same algorithm, but there is just one difference in this algorithm. That is, in step 1, instead of selecting one of the cities randomly, now what do? We find the shortest distance in the whole table, in the matrix. If there are more than one shortest distances, we select, we break the ties arbitrarily. So if you look in this table, the shortest, of course, there are zeros, but those zeros are going from 1 to 1 or 2 to 2. So we are not allowed to do that. So do not just consider this diagonal here. Other than this diagonal, you need to find the shortest. And if you see from 2 to 1, we have 2, and from 6 to 3, we have 2, and there are no others. So there are two same values, same shortest distances. We need to select one of them, and here it says break ties arbitrarily. It means that if there is equality, if there are alternatives, select one of them randomly. And here, let's select this city 6, so this one. Okay. So what do we do when we select it? In step 2, it says that set the source city as the starting point and the other one as the current city. So 6 becomes the source and 3 becomes the current. Okay. So what do we do? Here we started from 6, and from 6 we are going to 3, and 3 becomes our current. So we already visited 6, and since 3 is the current, we don't consider this column as well. And now the rest is the same. So what do? From 3 we find an unvisited city. So this one, this one, this one, this one, and this one, with the shortest one, and the shortest one is this. So from 3 we are going to 5. So 5 becomes our current city, we will not look at this column anymore. Okay, and 5 will be our current city. We can delete this one. And from 5, we will look at the unvisited cities with the shortest distance, which is 1. Okay, so 1 is our current city, and from 1, again, we will look at the unvisited cities. It can be 2 or 4 or 7, and we see that 2 has the minimum, so 2 becomes our next city, which is current. Okay, then from 2, I will not look this 1 anymore and 2 anymore, and we can go to 4 or 7, and 4 has a shorter distance. Then the next current will be 4, and since we have only one node remaining, 7 will be the last one. Okay, so this is basically the output of this alternative. Okay, so if you want to calculate the objective function, again you will do the same thing. Going from 6 to 3 has a distance of 2, then 3 to 5 has a distance of 7, and etc. So you will do this calculation, and when you find it, the objective function value will be 101. Okay, so we had two alternatives for TSP. Basically, they are both have the same idea, but the starting point was different, and with that difference, we improved the objective function value. And if we compare these two, we see that the first alternative has an objective function value of 111, and the second one has 101. So for this instance of the problem, we say that alternative 2 is better. But again, in a different instance, alternative 1 can be better than alternative 2. And we cannot say that this 101 is an optimal solution because there is no guarantee of this one. This is just a heuristic algorithm. Okay. I will show you another example from machine scheduling. So let's consider a single machine. We have one machine and we want to process 5 different jobs on this single machine. And the processing times of these jobs are given here. The processing time of job 1 is 5 minutes. Processing time of 2 is 12 minutes, and etc. We are given these information. The question is, find the sequence of these jobs, the processing sequence of these jobs on the machine, so that the completion time, total completion time of the sequence is minimized. We talked about this problem, if you remember, and the total completion time is this. For example, assume we have one job. Let's say this is our time axis, and this time starts at 0. Let's assume that job, let's say 3 is started here, and its processing time is 3, it's finished here. Then let's assume that job 5 follows it. Okay, its processing time is 5 units. It means that from 3 this goes to 8, and let's say job 2 follows this. Okay, and the processing time is 12 units, then it goes to 20. Okay, the completion time of job 3 is 3. Okay, we represent it as completion time of job 3. Completion time of job 5 is 8, and completion time of job 2 is 20. And the total completion time is the completion times of all of these jobs, which is 3 plus 8 plus 20, which is 31. So this is just an example. I didn't write the rest of the schedule in order to show you how we calculate this objective function. So it's 31 is the total completion time, and we want to find the sequence of these jobs so that this total sum is minimized. And there is a very easy heuristic algorithm for this one. It consists of only one step, and it says that sort the jobs in increasing order of processing times, which means that we need to find first the job with the minimum processing time. So this is job 3. So it becomes our first job. And then we need to find the next job with the second shortest processing time. And we see that job 1 and job 5 both have the same processing time, which are 5. Since there are no rules stated here, we can select any one of them randomly. If you like, you can say that job 1 is the second. If you like, you can say job 5 is the second. So I will say job 5 is the second, and job 1 will be the third, and job 4 will be the fourth, and job 2 will be the fifth. And that's all. It says that this is the schedule. So let's see what kind of a schedule it's. So again, let me sketch. This is our timeline. Okay, we start from time 0 and we start with job 3. So job 3 goes until 3. Then we continue with job 5, and job 5 has a processing time of 5, so it goes to 8. Then we have job 1, and job 1 goes until 13 because the processing time is 5. And then we have job 4. Okay, job 4 goes until 20. And then we have job 2, which goes until, let's say this is 32. And what is the objective function value corresponding to this? Basically, it is the summation of the individual completion times, 3 plus 8 plus 13 plus 20 plus 32. So this makes 76, I guess. You see, with just single step, we come up with a feasible solution, and this is the algorithm. But what's important about this algorithm is this algorithm is known as the SPT heuristic, SPT algorithm, which means shortest processing time first, or simply shortest processing time. Okay, so for this problem, if you want to minimize the total completion time, so be careful with this definition. If you want to minimize the total completion time, not make span, not lateness, not any other thing, just the total completion time. And if there is no release times of the jobs, no ready times, all of the jobs are ready at time 0, which is this problem exactly as it is. Then this SPT algorithm is not a heuristic algorithm. It gives you the optimal solution. It's an exact algorithm. Exact algorithm for this problem. Be careful. You can use SPT algorithm for another case, for another definition. In that case, it will not be an exact algorithm. It finds the optimal solution for this definition of the problem, which means that this 76, in fact, it is optimal. There is no other solution with an objective function value less than this one. Okay, you see, in fact, in order to find the optimal solution to a problem, we don't just need to go through the branch and bound algorithm or the cutting plane algorithm. There may be some other algorithms like this which provide you the optimal solution. And last, in the previous lecture, I told you about the polynomial time algorithms and etc. So if an algorithm finds the solution in polynomial time with respect to the problem size, then that exact algorithm is a polynomial time algorithm for that problem, and it's very important to come up with such an algorithm. Okay, so SPT therefore is a very important algorithm. Basically, it just sorts, and the sorting time is simply, we call it order of n log n time. This n is the number of jobs. Okay, so the running time of this algorithm is order of n log n. It is polynomial and very efficient polynomial. It is less than order of n square. Okay, it is less than an n square algorithm, larger than order of n but less than order of n square. So it's a very efficient algorithm, and it's very important. But the thing is, you need to what you need to understand is branch and bound, cutting plane algorithms, they are exact algorithms, but they are not the only exact algorithms. For different problems, for specific problems, you may come up with other exact algorithms. This is an exercise for you. In fact, it is the set covering problem. The formulation of this problem is given here. Basically, there are 4 alternative locations to place, let's say, some emergency facility. It can be a fire station. And these 4 alternative locations must serve the regions, and the restrictions related to those regions are given in these constraints. What I want you to do is try to develop 2 alternative construction heuristics for this problem by yourself. Okay, 2 alternatives. It can be a variation of each other, like in the TSP case of how we did. Then please try to write the steps of these algorithms as we did, as I gave you. For the knapsack problem, I gave you 3 different steps, pseudocodes. For TSP, I gave you the steps of the nearest neighborhood and its variation. Okay. For SPT, again, I gave you the step. Like those, write the steps, the pseudocodes of these algorithms. Please try to write it as correct as possible using those repeat and loops statements. And then solve these algorithms with both of these alternative heuristics that you develop and write their objective functions. Try to compare them. Okay. And it will be a good exercise for you to understand how to develop heuristic algorithms for different problems. Okay, so we talked about the construction heuristics in this video lecture. In the following one, we will start talking about improvement algorithms and local search algorithms.